Hello again. In this lesson, we will discuss software-defined networking, SDN, in more depth. For most of the Internet's history, the network layer has been implemented in individual distributed devices, routers. These routers incorporated proprietary network operating system software to run routing protocols and control device switching functions. Different network and higher layer functions, such as firewalls and load balancers, were implemented either in separate devices or incorporated in proprietary network operating systems of different vendors' routers. As the networks grew larger, they became more difficult to manage. Around 2005, network experts started to rethink how best to implement the network layer function. These experts proposed to emphasize the role of software in running networks through the separation of the data forwarding plane from the control plane. They coined the term for this software-defined networking, or SDN. There are two approaches to implementing the control plane. The first case, each router runs its own control plane. Or the second case, using a centralized controller. The next two slides, which depict the two approaches, should be familiar as we discussed them last week. The first slide depicts the traditional method. Each router runs the routing algorithms. Network routers interact with each other so that each router can compute the forwarding tables. The second slide shows that routing algorithms are running in a logically centralized controller. The controller is interacting with control agents in the individual routers to compute the forwarding tables for all the routers. As mentioned before, managing a large-scale network is difficult. By centralizing the programming of the control plane, the routing function can be managed from a central location instead of configuring each individual router. This saves manpower and significantly decreases router misconfigurations. The centralization also gives better control and flexibility over the network traffic. Also, this allows for an organization to migrate away from vendor-specific devices. What is happening to the network layer is analogous to the evolution of mainframes to the PC in the 70s and 80s. Mainframe computers were proprietary with totally closed interfaces. Applications ran on an operating system and hardware provided by a single vendor. The development of the microprocessor in the 1970s changed things. It split up this monolithic structure. Although the industry eventually coalesced to just a few microprocessor families and operating systems, the open interfaces between the microprocessor and the OS and the applications fostered rapid innovation, and it created a huge industry. Some hope that SDN will grow into a rich ecosystem, leading to another great innovation push. Let's look at some of the issues that traffic engineering encountered under a legacy network layer approach. In traditional routing, the network operator had limited tools to refine network flow. The routing algorithms are based upon link weights, which limit the ability to easily direct traffic along specific routes. The routing algorithms are based upon link weights, which limits the ability to easily direct traffic along specific routes. Load balancing with most traditional routing algorithms is very limited. OSPF, BGP, and RIP can only load balance across equal cost paths. With just destination-based forwarding, routing different types of traffic, such as real-time traffic versus web, can't be done. The separation of the control plane and the data plane in the SDN allows for generalized flow-based forwarding that facilitates better traffic engineering. The control plane functions are now external to the data plane switches, as are other network control applications, such as access control and load balancing. With SDN, the data plane switches are simpler. They are commodities, saving on acquisition and maintenance costs. They are essentially hardware devices built around a fast switch fabric and memory for the switch flow table. The switch operating systems are much smaller. The key software components are an agent and an API for the switch to communicate with the centralized controller. The switch and the controller communicate via a specific protocol. OpenFlow is an example of this. The network operating system is the heart of the SDN controller. The controller must be aware of and manage the state of the network. The controller interacts with the network control applications via what is called the northbound API. The controller manages the data plane switches via the southbound API. For resilience, the logically centralized controller is designed to be implemented as a distributed system, which incorporates a number of physical controllers that may be in different locations. This provides the high performance, scalability, and fault tolerance required for a 24/7 operation. Network control applications reside on the northbound side of the SDN controller. Some implementations divide the control plane into network control applications plane and a controller plane. Via the API, these applications can be delivered either through the software controller vendor or a third party. The Conceptual Sdn Controller is composed of 3 layers. The interface layer communicates with network control apps via the northbound interface. Besides incorporating a map of the network, this layer is composed of a few other components, including the RESTful API and the intent framework. REST stands for Representational State Transfer. A RESTful API is based upon a web standards architecture and uses the HTTP protocol. The idea of the intent framework is to tell the network what is needed, not how to do it. Let the controller figure out how to translate these policies into network configuration. For example, if an application needs extra bandwidth or a primary channel, the controller takes this information and makes the necessary configuration changes on the devices in question. The heart of the SDN controller is the network-wide state management layer. Here, the detailed picture of the network is kept in a distributed database. A communication layer talks with the control switches to the southbound interface using standard protocols. As I mentioned before, there is an open standard communications protocol named OpenFlow, through which the SDN controller can control OpenFlow-enabled switches. This standard is maintained by the Open Network Foundation, a user-led organization dedicated to the promotion and adoption of SDN. This standard is maintained by the Open Networking Foundation, a user-led organization dedicated to the promotion and adoption of SDN. OpenFlow is not an IETF standard. OpenFlow uses TCP to exchange messages. The OpenFlow channel can be secured using TLS, Transport Layer Security, but the OpenFlow specification does not mandate it. Note that TLS is the successor to SSL, which was discussed in Chapter 2. From my perspective, this security feature should be mandatory. A hack into the OpenFlow communications channel would be disastrous. In OpenFlow, there are 3 classes of messages. The first is controller to switch. The second is an asynchronous type message, switch to controller, and third type is symmetric. The controller to switch messages are initiated by the controller and, in some cases, require a response from the switch. This class of messages enables the controller to first determine current switch features, particularly on startup. Second, to manage the logical state of the switch, including its configuration to add, delete, and modify flow entries. Also included in this class is the packet out message. This message is used when the switch sends a packet to the controller, and the controller decides not to drop the packet, but to direct it to a specific switch output port. The switch-to-controller messages are sent without solicitation from the controller. This class includes various status messages to the controller, such as a port status change. Also included is the packet in message, which may be used by the switch to send a packet to the controller when there is no flow table match in the switch. There is also a message type to inform the controller about the removal of a flow entry from a flow table. Note that network operators do not directly configure the switches by explicitly creating OpenFlow messages. These messages are generated by a higher level program at the controller. Included in the symmetric messages are a hello message, which is exchanged between the switch and controller upon connection startup. Another type of symmetric message is the echo message, sent from either the switch or controller to verify whether a connection is alive. It can also measure the latency or bandwidth of a connection. Let's look at an example of SDN interactions. In this example, switch S1 notifies the SDN controller that it has experienced a link failure. Next, the controller updates this link status info and then calls upon the routing application, in this case Dijkstra's algorithm, to recompute the routes affected by the link failure. The routing application then extracts the information about the network graph and link status from the controller and computes new routes. In the fifth step, the routing app and the SDN controller work interactively to compute the new flow tables. Finally, the controller passes the new table information to all the switches that need updating. The concept of SDN is less than 20 years old. Much progress has been made, but there are still challenges before SDN is deployed on a broad scale. Only 15% of the companies surveyed in 2018 have deployed or are piloting SDN. ISPs are more progressive. 87% of the large service provider will have deployed or are evaluating deployment by the end of this year. There are many challenges in moving from a conceptual software control plane to a truly reliable, scalable, and secure distributed system. There are multiple new areas of research, such as extending SDN to other areas, such as media caching and inter-AS environments. In the next video, we'll talk about two protocols used for network management and diagnostics.